Now we have a very beautiful question here. Simple, subtle, but really beautiful. One phrase in this question is what adds to the beauty of this. A body falling under gravity, falling under gravity. Now, the beautiful part of this is, I mean, you might be wondering why am I so excited with this question? Um, because okay, let's do one thing. Now, what I'll do is I'll take you through the solution. I try to solve this question using two to four different methods, right? Four different methods, and then we'll use one more method to verify the fact that this falling under gravity here is under the assumption that the body is from rest, is from rest and is not thrown downwards. Now this you must be able to get an intuitive understanding regarding this. It is not given in the question, explicitly said in the question that the body is released from rest. Neither does it say that it is released thrown downwards. So what is the value of u that we are going to take from point 2? Right. So this is one of the questions that that we come across much often. So yes, that's one part of the question. More on this when we solve this in detail. To visualize this, we have point O, which is considered to be the point of release here. The object travels distance to point A, and then from point A to point B, and we have the ground here. From the question, we have point A to point B as 80 meters, and the time taken to travel from A to B is 2 seconds. My bad, it's not 81, it is 80. Oh, sorry. Oh, wait. This was unnecessary here, right? Sorry. Okay, separated by 80 meters. Yeah, so we have 80 meters in 2 seconds, point A to B and point O. Okay. Now, the question says a body falling under gravity. Now, when we say that a body is falling under gravity, it does not automatically mean that the body starts from rest. What does falling under gravity mean otherwise? Very, very, very important. Why? This is crucial. This is way crucial because it is this falling under gravity, meaning that gravity is the only force acting. It is this part which will help us solving this question using conservation of mechanical energy and work energy theorem. Okay. Now, some of us might be here for the first time. So I presume that you're here for the revision of class 11 portions, and therefore you wouldn't have reached the topic work energy and power and conservation of mechanical energy. So don't worry. I will take you through a brief part of this, and I'll also explain you what these two theorems are and when to apply them and when not to. Although you will not be able to get the complete understanding of this, you just have a rough understanding, and then when you start doing solve questions on work energy power, the understanding would become deeper. Okay, but as of now, it would be good to understand that gravity is the only force acting is the fundamental criterion for solving this question using conservation of mechanical energy and work energy theorem. Okay. This otherwise means that the body is in free fall. Now, when the body is undergoing free fall, right, which means the body is falling under gravity, there could be three possible cases. Case number one, it is just released from rest. Or case number two, it is already moving downwards and we just started observing the motion during the downward motion. Or case number three, thrown downward with some initial velocity. Right? And in this question, release from rest is the correct assumption. So you might be wondering, how is it that? we'll definitely have a detailed look into that. And we'll also prove that thrown downward with the velocity does not match the given data in this question, and therefore we will validate that it is released from rest. And that's the beauty of it. Okay, right. Now, why do we assume that the body is dropped? I'm not talking about the validation part here. We will definitely validate it. That's a totally different story altogether. But generally, when we solve questions based on the topics, based on physics in general, a body falling under gravity covers 2 points A and B separated by 80 meters in 2 seconds. This does not say start from rest, but we assume that the body starts from rest at point O. Okay? There was no mention of any initial speed. So, when there is no mentioning of any initial speed, the standard assumption in general physics is that the body starts from rest, unless stated otherwise. Okay. Now, I don't want you to make a note of this statement here. That really doesn't make sense here. We don't need this part. Give me a second. Right. So yes, I would also suggest you that, as usual in any question, please make a note of this along with me. Okay, would be time consuming now, but would be really effective the coming future when you solve questions. So, if a question wanted you to use an initial speed, it would explicitly say so. For instance, a body is thrown downward with velocity 5 meters per second. A body is projected upward with or maybe with some velocity, or it is already moving with some velocity. Since these kind of phrases are not mentioned in this question, instead which says a body is falling under gravity and does not mention any motion or speed, therefore we assume that the body is dropped from rest. However, it is important to validate this assumption. We'll come to that part after we discuss all the 4 methods. 1, 2, 3, 4, 5 actually. Yeah, 4 methods. Okay. Now, what are the 4 methods that I'm talking about? We could solve this question using equations of motion or conservation of mechanical energy, which I find is the most beautiful one here. Very similar to this is work energy theorem, but both of them will involve velocity calculation. We'll also do this question using the graph analysis. This is perhaps, I would say, is way more beautiful. It is way more beautiful than conservation of mechanical energy. This is my favorite, in fact. And then we will check for the consistency of the data, and therefore we will validate our assumption that the body is indeed starting from rest. Yes. Now I do understand that you have lots to write. I do understand. So maybe you can make use of this flowchart. A body falling under gravity can be approached in 2 different sections, 2 different types. Concepts in motion in straight line using equations of motion or graphical analysis. To be more precise, this is integration or area under the curve. And then we have work energy theorem and conservation of mechanical energy as 2 separate concepts in work energy power. Of course, I mean the 2 different chapters. Right now, this is how you interlink your concepts. This is how you get very familiar with the question. This is what enforces confidence in you, the command over the subject. Okay. Now, so this is what we will go through in general. Now let's come to the visualization portion one more time. So let us try to understand that the given data one more time. So we have the ground, an object is dropped from O, the corresponding velocity is VO, the body reaches point A, the corresponding velocity is VA, the time taken to travel from O to A is T1, and the corresponding displacement in T1 seconds is S1. Body travels further from A to B, the corresponding velocity may VA and VB. And the travel from A to B takes time T2, which is 2 seconds, and the displacement from A to B is 80 meters. The body has not yet reached the ground. Okay? We will first consider the first path. I could maybe write here. Oops. Motion of the body along OA. Motion of the body along OA. Applying equations of motion, we have v square minus u square is equal to 2as. And you are correct to guess that when we apply the concepts in work energy power, we'll be using the same motion along OA, but instead of using equations of motion there, we'll use law of conservation of mechanical energy along this path. Okay. Now, what is v square? Is the final velocity. What is the final velocity? Velocity at the final point. What is the final point? The point A. So the corresponding velocity is VA. What is u? Is the initial velocity. What is the initial point? What is the initial velocity? It is the velocity of the object at the initial point. What is the initial point? It is the point of dropping, which is O. So u square is VA square, u square is VO square. What is acceleration? Now, this is where things become more important. Since the object is falling under gravity, right? The body is experiencing acceleration. And therefore, the value of acceleration would be plus g. Another way of looking at it, the body is traveling downwards. Initial direction of motion is also downwards. Since both of them are downwards, acceleration would therefore be positive. Right? Okay. Corresponding displacement here is S1. What is S1? S1 is the displacement from O to A, SOA. Plus G is 10, 10 into 2 is 20. Since it is dropped from rest, this becomes 0. And therefore, V square is equal to 2. Sorry for the issue. So therefore, V square becomes 20 into SOA, right? So this relationship is something very important. V square is equal to 20 into SOA. Now what we'll do is we will consider the visualization part again, and everything else remains the same. And we have now derived that VA is related by VA square is equal to 20 times S1, which is SOA. Yes, nothing conclusive so far, which means we'll have to consider the rest of the problem as well, which is the motion along AP. To do that, we consider the motion along the path AB from point A to point B. And we use the equation S is equal to UT plus half AT square. what is S here? S is the displacement from A to B, which is the vertical displacement here, S2, or which is, okay, which actually I should have written it like this, right? Which is S2 is equal to SAB. So this is actually SAB, right? What is U? U is the initial velocity. What is initial velocity? It is the velocity at the initial point. What is the initial point? It is point A. Therefore, what is the corresponding velocity? VA. So what is the initial velocity? Initial velocity is VA. Initial velocity is VA. Right? What is acceleration? Again, the initial direction of motion is acting downwards. Right? Acceleration is acting downwards. Therefore, acceleration is equal to plus G. Or if we were to use the arbitrary scale here, downwards is taken as positive and upward is taken as negative. In any case, acceleration is plus G in this question. So half into G becomes half into 10, which is 5. Given in the question that the time taken is from A to B is TAB is 2 seconds. So T square AB becomes 4. 5 times 4 is 20. 80 minus 20 is 60. And therefore, VA becomes 80 minus 20 is 60. 60 by 2 is, 60 by 2 is therefore equal to, 60 by 2 is therefore equal to 30. Right? So we will come back to the first part now, which is from the point of drop O, to the initial point A. And along this path, we have already derived that VA square is equal to 20 into SOA. And just now we've derived the value of VA is equal to 30 meter per second. And now we can plug in this VA, the equation here, which gives us VA 30 square is equal to 20 into SOA. 30 square is 900. Now 900 by 20 is 90 by 2, which is 45. Therefore, the answer to this question is starting point, distance of point A from point B is 45 meters. Okay? Right now, so now let us come back to what we're trying to say. So we have done the question using equations of motion. Now I'm not going to come to the area under the graph for a while because it will be more or less in the same chapter, right? And let's do something different. It's been a while that I'm doing questions from motion to straight lines. So maybe we'll try to work out questions on the same question on work energy theorem, then conservation of mechanical energy. We'll come back to area under the graph. Okay.